So now that we've gone through our different factoring strategies and how to use each, we need to take a look and consider how can we choose which factoring strategy to best use that will save us the most time and effort when we're working through. So there are many factoring strategies, and we have covered them in previous lessons and in last lesson. Now, if we're approaching a problem, first we need to identify what kind of a problem it is that we're working with that we need to factor in order to choose our strategies. So if we look at our problem and it looks of the form, let's say it has an AM plus AN, and maybe there are more terms, maybe plus AP, then I can factor something like that. Basically what I'm noticing here is the common factor, if you will, of each term, where A is common to each term. Since A is common to each term, then we can factor it out. This would look something like A times M plus N plus P. And as an example, actually this might be a little bit easier with examples. Actually, let's not worry about that because we'll cover those down below. Now, next we're going to take a look at a difference of squares. Well, a difference of squares, again, I'm going to go pretty quickly through these because you have covered them. We have covered them already. A difference of squares looks of the form a squared, minus b squared. And that is, we have two square terms that are being subtracted one from the other. And when we factor this, it looks of the form a plus b times a minus b. And we can keep going. If we're working with a perfect square, it will look something like a squared plus 2ab plus b squared. And if it looks like that, that's what it will look like if we have a positive perfect square. Or if we have a negative term involved, then we're going to be looking at something that looks like a squared minus 2ab plus b squared. We notice the first and third terms in each are positive. It's just the middle term that changes. So the first one would factor into a plus b squared, and the second one would factor into a minus b squared. The form an plus bn plus am plus bm. And we would factor something like this. And really what we're noticing is that the first two terms share a factor n. The second two terms, or the final two terms, share a factor m. So this would factor into, really in two steps. If we're looking at it carefully, we can look at the an plus bn and the am plus bm. So we would be left with a plus b times n plus a plus b times m. And this shows up when you're working with decomposition, which is a common strategy used for complex trinomials down there. And this would factor even further. We would recognize the a plus b term to both the first half and the second half of what we're working in here. The a plus b is here and the a plus b is here. So that would simplify to a plus b times n plus m. So it's like we factor out this a plus b afterwards. Now, moving on, a simple trinomial, and I realize I'm running out of space a little bit here. A simple trinomial, let's write that over here. A simple trinomial will look of the form x squared, let's keep the coloring consistent. This will look of the form x squared plus bx plus c. And when you're factoring something like this, you're looking for a number that multiplies to c, a number that adds to b, and you can break that down in order to follow it. Your final answer to a question like this would end up x plus something times x plus something. And really that's plus or minus something depending on the sign of the final term there. And then a complex trinomial, and that's perfect. Now again, you may have a different strategy to work with simple trinomials. I've seen a common cross where we write the B and C in here, or else I've seen it done by looping. Whichever your strategy, that's great, but we just need to be able to recognize what a simple trinomial looks like, and that's shown by the x squared plus bx plus c. Now a complex trinomial is very close. It's very similar, obviously, because it's a trinomial as well. The only difference is we have an a term that's not equal to 1 here in front of the x squared. So ax squared plus bx plus c. And complex trinomials, you can solve those as well by looping or by decomposition, or whichever strategy you like. We just need to be able to recognize that it is a complex trinomial. Now, you'll notice that when you're working, that some problems can fall into a few different categories. So they might fall into common factoring. They might also be complex trinomials. They might also be perfect squares. That's actually possible. We could have 1, 2, and 3 all in the same problem. If you're noticing those, I've written them in a strategic order here. It basically, it goes from easiest to most difficult as you go further down. So if it's a complex trinomial and you notice a common factor, you want to deal with the common factor first, and you might not have to deal with the complex trinomial later. Likewise, a perfect square actually is just a special example of a complex trinomial or a simple trinomial. And so when you're working with a perfect square, then you are going to, if you notice that it's a perfect square, great, you're going to save yourself some time. Otherwise, you'll be forced to handle it like a complex trinomial, and that will take more of your time, more of your effort, and it will leave then less time and less effort for other problems. Now let's use these examples below and just try and recognize what kinds of problems we have based on that quick description that I put up above for each. So the first question here I recognize as a difference of squares because I see that my first term is 49x squared. And if I were to square root that just to see if it's a square number, I would find that that equals 7x. Likewise, the second term, 121y squared, if I were to square root that, I would find it equals 11y. And I see my subtraction sign in the middle. So this is a difference of squares. We're not going to solve it right here. We just want to be able to recognize which strategy would be the most effective way to solve it. Next, we have here a question. Let's take a look. Is there a common factor? No, because my first term is x squared, my final term is 25. There's nothing in common there. Is it a difference of squares? No. This has 3 terms, right? 1, 2, 3, and a difference of squares only has 2. Is this a perfect square? Well, let's check. My final number, it is a square number, so that checks off one box right away. My first number is also a square number, so now I need to check, okay, is my middle coefficient, is that equal to the square root of my the square root of my first coefficient times the square root of my third coefficient times 2? Well, let's check. The square root of my third coefficient, square root of 25 equals 5. Okay, the square root of my first coefficient, the square root of 1 equals 1. And 5 times 1 times 2, remember we need to multiply that by 2 because that's what's shown in our equation up here. We need to multiply that by 2. We get to 10. Okay, so since our b term is 10, this is a perfect square, which is easier to solve than a simple trinomial because we can just follow a pattern that we know. Looking forward, for part C, okay, do we have a common factor involved? Well, it looks like it actually. It looks like there's a b plus 3 here and a b plus 3 there. So since there's common factoring involved, we can just handle it like so. Now, this one is actually a partially solved grouping problem. So if you recognize that as grouping, then that's fine. That's just the way your brain works through it. That's fantastic. You can use that to solve it. Lastly, we have a final one here. Is there a common factor? No, because 15, I happen to know, shares no common factors with 8. Okay, well, is this a difference of squares? No, this has too many terms. is this a perfect square? We can quickly check. 15 itself is not a square number, nor is 8, so this is absolutely not a perfect square. There are only 3 terms, not 4 terms, so we're not going to solve this by grouping. So now we just need to identify, is this a simple trinomial or a complex trinomial? We can look at the first term here, realize that it's not equal to 1. A doesn't equal 1, so this is a complex trinomial. So we would solve that, again, using your favorite strategy, whether that's decomposition or looping or however you like to think about it. Now, moving forward a little bit, let's consider the number 72. And I chose this strategically. We just want to try and break it down into its factors, and we want to break it down as much, as deeply into its factors as we can. So if we start off with 72, we can think of just a few factors of 72. And I can show this in a couple of different ways here. Let's see. The number 72. Okay, well, 72, I can see right away it's an even number, so it's 2 times something. And if I check my calculator, 72 divided by 2, that equals 36. So 72 equals, and I'll show it with brackets, equals 2 times 36. Good. Now, can we break that down even further? I happen to know 2 is a prime number, and a prime number, the only factors of that are 1 and itself. So I'm not going to be able to break that down further, but the number 36, I can. 36, I recognize, again, as an even number, and since it's an even number, I can divide it by 2. So another way of writing 72, so 72 equals 2 times 36, and it also equals 2 times, we'll break up this 36 now. 36 is 2 times 18. Okay, well, let's keep going with this pattern. We'll see how often it works with 2. I can see right away that if I'm looking at the 18, I should be able to, I know that's an even number once more. So this equals 2 times 2, and then we'll break down that 18. Well, 18 is an even number. If I divide that by 2, then I get 9. Perfect. So I'm just trying to break it down into prime numbers here. I'm seeing how much I can break this down. Now, I'm left with so many 2's here. 2 times 2 times 2. Okay, and then I have a 9. Now, 9's not a prime number. I can break that up even further here. So the 9 can be broken up into 3 times 3. Right? Now, at this point, I notice that I have 5 different factors that have come out of just one number, the number 72. So I can list them off, and I can actually collect the ones that are similar. So I could rewrite this as 2 to the power of 3 times 3 to the power of 2. Now, I just wanted you to see how we could keep breaking that up. And as we rewrote 72, we had to keep writing all of the factors that we previously found. So you notice this 2 that we found right away, it stayed consistent all the way down the solution. That's going to be the same way we set up our problems if we're factoring an expression when we're trying to find it in a fully factored way. Now, let's move on. So an expression is fully factored only when each factor can no longer be broken down. And we could see up here we only stopped when each factor could no longer be broken down. So we'll use this idea to try and fully factor the following. So I can see here, using my strategies up above, I notice that there is a common factor. And again, that's the first thing I'm looking for. So there's a common factor. I'm going to write CF for common factor off to the side here. So the common factor I see is 3. So I can break that down. Well, that equals 3x squared minus 2x minus 144 divided by 3, which if I put that into my calculator, I should be able to handle it no problem. That equals 48. Okay. So now I have, you'll notice initially it was a complex trinomial. So I could have handled this like a complex trinomial, and it would have taken me a lot of work to try and solve. I'd be looking at 3 times negative 144 and try and find some numbers that multiply to that. It's a bit of a headache, but now it's much easier. Now I have a simple trinomial. So I'm going to write ST for simple trinomial, and I'll solve that. Again, you can use your favorite method. I'm going to use this here. So we need numbers that multiply to negative 48 and add to negative 2. Okay, so let's break negative 48 down into its factors. 1 and negative 48, 2 and negative 24, 3 and negative 16, 4 and negative 12, 6 and negative 8. Okay, there we go. And actually should have left myself a little bit more space here, so I'm just going to move this over. Perfect. All of this work is still solving example A here. Now, I could break it down to my other factors, and you know what? I will list them all. I can list them again just by switching the signs here. So that's negative 1 and positive 48, negative 2, positive 24, negative 3, positive 16, negative 4, 12, and negative 6 and 8. And then let's add up all of the pairs. So we're adding up pairs across in a row like this. We get negative 47, negative 22, negative 13, negative 8, and negative 2. Perfect. We just found the one that adds up, the pair of numbers that add up to negative 2. So we're going to take those two numbers out. That's kind of why I left that n there. You don't need to use that. If you prefer to stop here, that's fine. But the numbers I found were 6 and negative 8. So that means that identifying this as a simple trinomial allowed me to factor this into 3 times x plus 6 times x minus 8. And there we go, it's completely factored. Now, I would like you to use that strategy, breaking it down, identifying which strategy you can use to solve B and C. And use that in the homework. We will try, when we're solving it, we can use kind of those shortcuts. So we can write CF if we can common factor it. We can write a difference of squares. We can write perfect squares. Grouping, maybe you could write that forward, a simple trinomial and a complex trinomial. But that way you can identify exactly which strategy to use. And as long as you can identify that, maybe you'll struggle sometimes to factor. That's fine, that's part of it. But if you know which strategy you're trying to use, and you know that the problem falls into one of those categories, and you're still struggling, then that means you probably just need to practice that strategy a little bit more, and you can know how to better direct your own learning. So if you have any questions on that, definitely let me know, but it should be pretty straightforward for you.